Before we get started, are there any questions over the homework? So with what we did on Tuesday, because we had ACT testing yesterday, what we're continuing on with is solving. And I think for some of y'all, because I think they're starting to actually randomize some of the questions on the ACT, especially the digital one, so you're not having the exact same test. I think at least one or two of a similar type, something like this, did show up in a form. But what we're wanting to do here is solve this exponential equation. We're trying to see what power, 2 to what power is 7. Now, if we wanted to, we can grab a calculator and try to figure this out. Because 2 to the first power is 2. 2 squared is 4. 2 cubed is 8. So if it had been 2 to the x equals 8, we could just say x is 3. We're good and fine there. But when we start getting to this point here, we're going to have to start trying to estimate, because we could say 2 to the 2.5, or 2 to the 2.7, or 2 to the 2.9, and start trying to figure this out as we go to try to get closer and closer. 2 to the 2.9 got us pretty close, so we can say 2 to the 2.95, and keep going in this way to try to get there. But it won't ever get us close enough to it or give us an exact value. So what we're going to have to start using is logarithms, these inverse functions with exponentials. Now there are some main steps to it. And the first, and a lot of what we do with this in exponentials and logarithmics, is try to get one term on either side. And try to get the variables all together, either in the exponents, inside the parentheses. We want one term on either side. It's the big goal. One term. Let's make that a little bit cleaner. One term on each side. And for this here, 2 to the x equals 7, we're good. We have the 2 to the x on the left-hand side. We got the 7 on the right-hand side. Now for exponentials, our main goal next is to get the variable out of the exponent. Because we want to get that variable out of the exponent for exponentials. For logarithmics, we need to get the variable out of the log, outside of the parentheses. We need to simplify the log. Now for us here, to do that, what we're going to do is apply a logarithm to both sides. Now we're going to use log, L-O-G, because the base is a number. If the base was E, we're going to use natural logs. And the log we want to apply to both sides is going to be a log base that's going to make that left side nicer. And what is the base of the left-hand side that we started out with? 2. So what I'm going to do is I'm going to apply log base 2 to both sides. Now log base 2 of 2 to the x, we went over this before, because we had, you don't necessarily have to write this down, log base b of b to the x was equal to x. And we just took that at face value, that that was true, this is how it works. But since then, we learned about the product property, or our power property. Power property says if I have an exponent inside the logarithm, we move it to the front. So really it's telling me that I have x times log base 2 of 2 is equal to log base 2 of 7. Log base 2 of 2 is 1. When the base and the number inside are the same, it is going to equal 1 because, again, all a logarithm is saying is the base to what power is what's inside the log. So here we're saying 2 to what power is 2? 1. 2 to what power is 2? 1. So really this whole thing is going to reduce to 1, giving me just x. Questions on how we got the variable out of the exponent? We're going to do a similar step to try to get that variable out of a logarithm, but instead of applying a log, we're going to apply a base to get that logarithm to simplify out. Questions on this so far? We ready for step 3? I'm going to say solve for x, but really we're solving for whatever the variable is, the unknown quantity. This is the last main step. We need to get that variable by itself. So looking at this here, is x by itself? Yeah, so is there anything else we need to do? No. So x equals log base 2 of 7 is the answer. And I will take that. I do want you to give the approximation because we can find the value of this here. The graphing calculator is very nice with it because we can hit the math button and scroll up or down to log base 2 of 7. Log base 2 of 7 is 2.80735499922. Realizing I went a little too far with the first here, because both those values are way too big. But we'd normally find this here, round to 3 decimal places, and see this is approximately 2.807. And we have both of these here. Homework and the test. Give me both, especially on the test. I want log base 2 of 7, and I do want the decimal approximation. Now, I'm not asking for both because I'm nitpicky or trying to be particular about this. But I've seen it numerous number of times. Y'all will get this right, but plug it in wrong. You'll get to the fact that x is equal to log base 2 of 7, and for whatever reason, plug it into the calculator wrong, this, that, and the other. And especially on the test, if this is wrong, but this is right, I'm giving you full credit for it. Okay? Now the question is why, yes? That seems odd, because the 2.807 is part of the answer, yes? But even if you get that wrong, I'm marking it right. What did this problem ask you to do? Solve each equation, yes? Is this solved? So what is the difference from going from here to here? You're finding, you're approximating that value, yes? Is that a part of solving? Yes. But did you already solve it? Yeah. So really, I feel like marking points off because you got this wrong is not a part of solving. That's calculator error. You solved it. That's not what I'm checking. That's not what I'm seeing. Calculator error. I'm not checking to see if you can make it in the calculator. I would like it. But again, if you got this, you solved it. Got this wrong, that's calculator error. That's not a part of solving. Especially for these here. Does that make sense? Now, if I'm asking you to evaluate this, and I gave you that to start, yeah, I do need the correct decimal approximation. Questions on this here? 3 to the x equals 8. Main thing we want first is to have one base on either side, one term on either side. So for the 3 to the x, I don't want anything being added to it. I don't want anything being multiplied by it. We need everything on the other side. And incidentally, we do indeed have that, yes? So since we got one base on either side, to get that variable out of the exponent, we're going to apply a log to both sides. But specifically, we want to apply log base what? 3. And as we just saw, we can do the same steps. The x is going to move to the front, telling me I have x times log base 3 of 3 is equal to log base 3 of 8. But log base 3 of 3 is what? 1. Really telling me I have 1 times x, or just x, is equal to log base 3 of 8. Now we can find the approximation for this here. So let's say we don't have the graphing calculator to pull out. We can still find this because of our change of base. Change of base formula. Log base b of x, if we want it in common logs, is log of x over log of b. Or if we want to put it in natural logs, it's the natural log of x over the natural log of b. So if we wanted to use the 30xs, or not have to plug it into the log base for the graphing calculator, log base 3 of 8 is the same as log of 8 over log of 3. So I can grab the calculator and say log of 8 divided by log of 3. Or if we felt like natural log of 8 over the natural log of 3 still gives us this 1.8927, 1.893. Yes.
Whenever we're solving the log base and the log base, we have to solve it in different.
No. Because the big difference in the question is, do we have to solve it differently for natural log or log base? No. The only difference between the two is that for natural log, the base is understood to be e. So we gave it a different notation. So realistically, the natural log of x is equivalent to log base e of x. So instead of writing it as log base e of x, we just say natural log of x. Good question. Questions on this here? We ready for the next one? 7 to the 9x. This looks a little different, but we're going to treat it the exact same as we've been doing. As the big goal, first main goal we want to do is get one term on either side, and we do. I'm rewriting it so I have a little bit of space for our second step to get that variable out of that exponent. And to get that variable out of the exponent, I'm going to apply a logarithm to both sides. And what's the base of our log going to be? 7. Because I'm trying to get that 9x out of the exponent, it's attached to that base of 7, so we're going to apply log base 7 to both sides. And we can write it out, but we know that log base 7 of 7 to the 9x is going to give us 9x. Telling us that 9x is equal to log base 7 of 15. Now at some would say we need to figure out what this is and go from there. Some don't. I am more the not so much, because log base 7 of 15 is not a nice number. It's an approximate. If we wanted to find its value, it's a non-repeating, non-terminating decimal. It's an irrational number. So for us to be able to continue on, we'd have to have that decimal approximation. We'd have to round and go from there. Leaving it does not change anything, because we're not done. We're not finished solving, because x is not by itself. So what we have to do is get x by itself. And since it's being multiplied by 9, we're going to have to divide both sides of the equation by 9. 9x divided by 9 would be x. And that's equal to log base 7 of 15 over 9. We can divide these logarithms by numbers, by terms, by expressions. Questions on how we got here? Now, if we wanted to do this in the graphing calculator, the first thing I would go is alpha y equals enter. I want that fraction first. And while we're on top, we can go to math, log base 7 of 15. And that is over 9. Telling us that the decimal approximation is 0.1542 or 154629167. Or if we go to 3 decimal places, 0.155. If we wanted to do the change of base, we could do log of 15 over log of 7. See what that is, divide it by 9 to get the exact same answer. Or if we wanted to put it all in at once, log of 15 over log of 7 all over 9 does give us the exact same thing. Change of base makes it look a little more complicated because we're having fractions and fractions, but it is the exact same process. Questions on any of this so far? Are we ready for what's next? 5 to the 3x plus 7 equals 311. Not any different, we've just added more steps to the solving process. Because 5 to the 3x plus 7 is equal to 311. Again, we're good. We have one base on either side. We don't have to move anything. We don't have to do any solving steps there. So we can go into our first main part of solving, or our next main part of solving, to apply a logarithm to both sides to get that variable out of the exponents. And for this here, we're going to apply log base 5 to both sides. Now the right-hand side is still going to be log base 5 of 311. The left-hand side, log base 5 of 3x to the 3x plus 7 is going to simplify to 3x plus 7 because it's going to move to the front and it's going to simplify out. Yes. Yes. Mm-hmm. Now there are, again, there's some cases where that wouldn't be the case, but as long as we get that base of the logarithm and the base of what's inside the logarithm the same, it simplifies to 1, leaving us with what's inside the exponent. Questions on how we got here? Is x by itself? Now we've got several things with x. And the first thing we're going to want to do with getting x by itself is our addition subtraction steps. So the first thing I'm going to want to do is subtract 7. Because 3x plus 7 minus 7, the positive 7, negative 7 is going to become 0, leaving us with 3x. Now it's going to be very tempting, or you might end up writing that we have log base 5 of 304, but that is not the case. Because that 311 is stuck inside the logarithm. It is a part of that log. Because when we calculate this, or we're calculating approximating it, we have to find out what the value of log base 5 of 311 is. Whatever that value is, we're taking 7 away from it, not the 311. And that is one thing you got to be careful with, especially typing it in. If you don't close that parenthesis off with that logarithm, it's going to subtract it first. We still have one other thing with x. We have the 3. So we have to divide both sides by 3, telling us that the value of x that makes this true is equal to log base 5 of 311 minus 7, all divided by 3. Questions on how we got this here? Alpha y equals enter. Okay, 7. Make sure it's log base 5. I would have messed that up. Enter. Alpha y equals enter. Log base 5 of 311 minus 7 over 3. It gives us approximately 1.144555382, or if we round to the third decimal place, negative 1.145. Wrong calculator. There we go. Questions on this here? Questions on anything we've done so far? I think for the most part we feel comfortable with this, yes? Now if we look at the next one, because this one here I think we've got. I want to look at this one. And the big difference is that the base is e, not a number. And there's a little bit more going on with it. Because if we look at this equation, we have 4e to the negative 0.3x minus 7 equals 13. I do not have one term, one base on either side, one term on either side. So before we can even start applying logarithms, we're going to need to get this e term by itself, this base of e by itself. So the first thing I want to do is add 7 to both sides, because our negative 7 plus 7 will simplify out, leaving us with 4e to the negative 0.3x equals 20. E is not by itself, that base is not by itself on the left-hand side. So what we're going to have to do next is what? We're going to have to divide both sides by 4. So really what we're looking at is negative 0.3x, e to the negative 0.3x is equal to 5. I'm just moving it over a hair. Now do we have one term on either side? So on these here, and they, for whatever reason, do it with e more than do with just a number base, we rewrite it and have a lot of stuff left next to it. Now because the base is e, the logarithm we're going to apply to both sides to get that exponent out, or to get the variable out of that exponent, is the natural log. And again, the properties of natural log are the exact same. We can move that exponent to the front. So our negative 0.3x is being multiplied by the natural log of e. And it's equal to the natural log of 5. And what is the natural log of e? One. That's kind of a way that I've remembered it or find it interesting. Natural log of e is indeed 1, because the base for natural log is e, so the base and what's inside the same, so it works out to be 1. Telling us is that there is 1, and negative 0.3 x is equal to the natural log of 5. Last but not least, what do we need to do to solve for x? Divide both sides by negative 0.3, because our negative 0.3x divided by negative 0.3 is going to be x, just x, and it's equal to the natural log of 5 divided by negative 0.3. Now, luckily, natural logs are a little bit nicer to plug into the calculator because the base is always e. Either calculator will let us take the natural log of 5 divided by negative 0.3, and it tells us it's negative 5.364793,041, or negative 5.365. Questions on this here? Are you ready for the next one? Three e to the x minus 4 equals 8. What can we do first? Add 4 to both sides. We've got to get e by itself, because our negative 4 and positive 4 will cancel, telling us 3e to the x is equal to 12. What next? We're going to divide both sides by 3, because again, e to the x is still not by itself. And 12 divided by 3 is 4. Is e by itself? Is that base by itself? I mean, we have the exponent of x, yes? But e, there's nothing else being added to it. There's nothing being multiplied by it. Nothing being divided by that base. So now we can apply the logarithm, which would be in ln, our natural log. Just like before, the x would move to the front, and the natural log of e is 1. Really telling us that x is equal to the natural log of 4. Unlike the last one, x is indeed by itself, so it's saying x is equal to the natural log of 4. Or if we wanted to find the decimal approximation, I can just ask the calculator what the natural log of 4 is, and it tells me it's 1.386 if we round to the third decimal place. Questions on this here? Questions on anything we've done so far? Do we feel comfortable with this base at e? Yeah, because here we just apply the natural log to both sides, add 3, divide by 4. and get that x is equal to the natural log of 19 plus 3 all over 4. Bless you. The other type that we're going to look at is this here, logarithmic. Because before, when we started off in exponential, we had a number, or e, which is still a number, to an exponent where the variable was in that exponent. We use logarithms to get the variable out of the exponent. Here, we're going to use exponentials to get the variable out of logarithms. Now, with logarithms, again, we want one term on either side. We want one log. If we have just one on the left, everything else on the right. If we have two logs and we can get them to be the same into one log using our properties of logarithms, we're going to do that. If we have several, and especially if they have the same base, we can even it out, as long as there's no numbers outside the logs. Because what we did Tuesday, our one-to-one property had one log on either side, we can get rid of them. That 3 being outside the logarithm kind of throws this apart. I need one thing on either side. Numbers, logarithms on the other. And one thing that we can do with this, once we get it set up in this form, one log equals numbers, is we're going to put both sides to the base of whatever the logarithm's base is. Since this is log base 2, we're going to put both sides to the base of 2. Because our 2 and the log base 2 are going to simplify each other out, leaving us whatever's inside the log. Telling us that 5x minus 17 is equal to 2 to the third power. Questions on how we did this here? Questions on any of this so far? Is 2 to the third a nice number? Well, we can check and see. 2 to the third is 8. Now, when I say nice number, I mean non-decimal number. Or it is a number that we don't have to write in exponential or scientific notation. Question? Now, if it had said that this was 2, we're putting 2 to the 700, yeah, that we're going to leave as 2 to the 700. That's way too big of a number. But 2 to the third is 8. We've gotten the variable out of the logarithm. We've gotten it out. Now we need to solve for x. We need to get the variable by itself. Now, because the variable is not a quadratic, we don't have an x squared. First thing we can do is add 17 to both sides. Telling us 5x is equal to 25. Then we would divide by 5. Telling us x is equal to 5. Doesn't show as much here, but we do need to be careful with logarithms because what's inside a log cannot cause, the value of this variable cannot cause the expression inside the logarithm to become negative. So if we were to check this here, log base 2 of 5 times 5 minus 17 is equal to 3. Now, especially on the test, if you wanted to check this, you can type that entire left-hand side into the calculator, let it do it for us, see what it is. If we did this by hand, 5 times 5 is 25. 25 minus 17 is 8. And log base 2 of 8 is indeed 3. Questions on this here? Questions on anything we've done so far? As we look at this next one, we have log base 3 of 10x minus 9 equals 4. Here we do have one term on either side. Now, even though we do have that 10x minus 4 here, or 10x minus 9 here, because it's inside the logarithm, it's still connected as a term. Log base 3 of 10x minus 9 is one whole term. The reason or way it wouldn't be one whole term is if we had plus 7 outside that parenthesis, something being added to it. We don't, so we don't have to worry about that there. Or if I had 4 times log base 10, or log base 3 of 10x minus 9, we would need to get that 4 to the other side. But we don't have that. We just have log base 3 of 10x minus 9 equals 4. One term on either side. So now we need to get the variable out of the logarithm. And to do that, we're going to put both sides to what base? 3. We're going to put it to the same base as the logarithm. And the reason we do this is because 3 to the log base 3 is going to simplify, leaving us with what's inside this logarithm. Telling us 10x minus 9 is equal to 3 to the 4th power. That should be a nice number. Let's see here, 3 to the 4th is 81. So really what we're saying is that 10 x minus 9 is equal to 81. Variables are out of the logarithms, but x is not by itself. The variable is not by itself. So what would we need to do next? We need to add 9 to both sides. Because our negative 9 plus 9 would cancel, telling us that 10x is equal to 90. And last but not least, we would divide both sides by 10, telling us x is equal to 9. Questions on this here? Now, luckily for us, these here are all going to work out, because if we were to check it, log base 3 of 10 times 9 minus 9, we're wanting to see if it equals 4. If I have the graphing calculator, I can go log base 3 of 10 times 9. Is it minus 9, yes? It does indeed equal 4. So it says that works, that is a correct solution. Questions on this here? I think we've got one left, don't we? Log base 2 of x minus 6 equals 5. Do we have one term on either side? We do. Now, the x minus 6 is kind of throwing us off because it seems like more than one, yes? But since it's inside those parentheses, inside that log, that's all connected as one. This is considered one whole term. And to get that simplified out, we're going to put both sides to the base of 2. Because our 2 and log base 2 are going to simplify, cancel out, leaving us with x minus 6 is equal to 2 to the 5th. And if I remember right, 2 to the 5th isn't 32. So we're saying that x minus 6 is equal to 32. We're going to add 6 to both sides, telling us that x is equal to 38. Questions on any of this here? Now, when we put both sides to a base, and especially like this one here, 2 to the 5th, there will be cases where we don't have a nice number. And that's going to be if that base that we're applying both sides is e. E is an irrational number, so no matter what I put that power to, or that e to that power, it's probably going to give us an irrational number. And if we have those, we want to save it to the very end before we start approximating. And that's it for this part. 9, 10, 13 through 16, 25 through 27, and 32.